They will initiate the virtual lamp lighting ceremony and bless this event with their presence. Thank you all of you. Now I would like to invite Ms. Anjali to introduce our esteemed resource person, Professor Fred Blaberg. Over to you, Anjali.
Good evening, everyone. I'm Anjali. It is my great honor to introduce our today's resource person, Fred Barberg. He is a famous professor from Denmark and works at Aalborg University. He is an expert in power electronics, which is very important in electrical engineering, especially for renewable energy and modern power systems. He has published more than 1,000 research papers and is one of the most cited researchers in the world. He has also received many international awards for his excellent work. He is also associated with IEEE and has contributed a lot to engineering education and research. Many students and engineers around the world learn from his work. We are truly lucky and proud to have such a great personality with us today. On behalf of everyone, I am warmly welcoming sir. Thank you. Over to Archana.
Thank you, Anjali. Now I would like to invite our respected Vice Principal, Dr. S.G. Kulkarni sir, to share his valuable guidance with us.
Respected dignitaries, Professor Frede from Aalborg University, Denmark, Dr. K. Shivshankar, all the office bearers from IEEE committees, all the participants of this international webinar seminar. Actually, we know the importance of renewable energy. Day by day, the energy crises are going on. We are presently observing that every day the energy requirement or dependency of the energy is increasing. There are n number of facilities are creating around us, and all these facilities are directly indirectly linked with the consumption of energy. Per capita energy consumption rate previously before 10 years ago, and if we compare today, then tremendous increasing this energy consumption has been increasing worldwide. As far as concerned with India, so more than 140 crores of population is there, and energy is the mostly required part because import of India is totally dependent on the energy. So renewable sources are very important, and it's very glad that today's our honorable speaker, Professor Frede, is a resource person in this particular field. He has large number of citations in this particular area, and truly we all are lucky to hear him on this platform of IEEE with SKNC Hegde College of Engineering's chapter. And I will not take too much time for this particular his session. I will request him to deliver this speech, and thank you very much, sir. Thank you, sir.
So
Thank,
now it's my turn, or yeah, please. Should I start?
Shiv Shankar, nothing is there, then let us continue.
And the next one.
Thank you, sir, for your motivating words. Now, there is one announcement to all participants who submit feedback after the session will be allowed to take the assessment. If participants not giving any type of feedback, they are not eligible to give any assessment. It's a time for the most important part of today's event. I would like to invite our esteemed resource person, Professor Fred Blaberg, to deliver his session and share his valuable knowledge with us.
Okay, thank you so much for this very nice introduction and also very nice words in general. And let me also use the opportunity here on behalf of the IEEE to say thank you very much for all your volunteering work and activities. That's I think that's very great. IEEE has always, for my life, been a very important place to meet peers and so on. Now, this is not my talk today, but I'm very happy to be here. Let me try to see if we are lucky again. We can share, and I just need in just let's see. Let's go up here. So now you see very well my screen, full screen, right? Just a confirmation. So I'm. Okay, so what I will touch and discuss today, this is what I would say one of the very booming areas in general in engineering, and that's of course in the energy sector. But the energy sector is extremely important for all other things, which I also hope you will get out of it. And that's both generation, transmission, distribution, and efficient use of energy. So today I will discuss with you some of the important topics on different aspects, and then at the end, let's say, come up with some conclusions which we can take a discussions about. Let me just use a few words on where I'm sitting today. I'm sitting up here in Denmark. I say up here compared with where you are sitting. Denmark is a very small country, about 6 million people, and you have here the map of Denmark, where Copenhagen is the capital, and up here is Aalborg. And Aalborg got a university more than 50 years ago, where the mission was to interact with the society, create value for the society. And thanks to that, we have a very, let's say, open-minded approach in our education and also research mindset, because we want to solve problems for the society. And that means also the students, they face another curriculum compared with classical curriculums, meaning that we have even a kind of, let's say, educational model, which is, let's say, named according to Aalborg University. We call it the problem-based learning model, PBL Aalborg model. Maybe the most famous, at least in some parts of the world, the poet Hans Christian Andersen is very famous for his fairy tales. Aalborg, as such, is a university with 22,000 students and with a budget around 400 million euro. And one of the, let's say, strong areas in general is in electrical engineering, where we have for many years been quite good ranked in some of the, let's say, ranking system, US News, as well as the Times Higher Education. Now the Times Higher Education has its normal, let's say, ranking system, but it has also have a lot of focus recently on what we can call the sustainable development goals, how universities are trying to approach that. And in that context, Aalborg University, thanks to the, let's say, the thinking of solving problems for the society, it has been ranked relatively high, as you can see here. Going into the topic of today, let me just start a little bit top level. As I see, and this is also driving my daily activities and so on, and that is to create value for the human being. And I think one of the announcements, one of the agreements, which for me says a lot about what we should strive towards, this is to contribute to the UN Nations Sustainable Development Goals. And there are 17, and I hope, and I not hope, I think many of you know them, and I think we can hardly disagree on them. But what is interesting for me is, of course, also to see where is power electronics as such, let's say, contributing to, as well as renewable, which are the topic of today. And they are directly on the spot. If we look through all them, renewable energy, number 7 is definitely clear. But also innovation and infrastructure, like illustrated here, responsible consumption, climate action, as well as this field is booming in many dimensions, giving economic growth in many aspects and also exciting jobs. And one way of, let's say, improving and moving faster and faster, in my opinion, is to let's say to do partnerships in that respect, and in that context, IEEE, in my opinion, is an important actor. If we look a little bit into the, let's say, into the future, and we talk about, let's say, power electronics, we talk about renewable. Let me just show this figure here, which is indicating what are the, what is, let's say, some kind of trend we are seeing in the society. And one of the trends is that we want to reduce the carbon emission into the atmosphere. And if for all kinds of aspects, and one of the biggest, let's say, contributor are of course the energy. And if we look at the final total energy consumption, where, let's say, the resources are coming from in order to do that. So this is an energy consumption, not, let's say, the usage as such, because there are efficiency considerations. Then what we can see here is clearly that we have a fossil fuel-based society. Electricity is only 20%, and biomass also contribute to it. Now there have been some, let's say, studies. How can we ensure that we do not have a too high temperature rise on the planet? And there is an organization called IRENA. They have tried to come with a suggestion, also what they think is technical feasible, and how should that then look in order to, let's say, accommodate this challenge we have with the temperature rise. And in such context, the figure will look like this, where you can see that we have, let's say, reduced significantly the fossil fuel-based part, as well as you can see that the yellow is now more than 50%. And then biomass still have some role to play, district heat, renewables, but also hydrogen is seen to have a, let's say, a major role to play, because this is a way also to store energy. And for that, we need electricity. So what we are fundamentally transforming the society is in, if we want to achieve this 1.5 degree temperature rise, be below, this is moving from a fossil fuel-based society to be an electrical-based society, where you can see the electricity is, it needs to be tripled as such. This is, I think that's very, very interesting. And a second thing is, of course, is also what we can see here is that the size is smaller in the future. And the main reason for that is that when we are using the fossil fuel, this is becoming changed to other fuel. And then, let's say, the process is much more efficient. And one of them is, of course, the transport. If that is becoming electrical, then where the efficiency is much higher, of course, given the condition that, let's say, it's based on something which is not carbon emission driven. This is a prognosis, let's say, some calculations in order to, let's say, be below 1.5 degree. However, this is maybe too, let's say, optimistic as such. What is maybe more interesting is what are the predictions in terms of electricity consumption on the planet. And there is our organization called DNV. They look very carefully at all countries, what is going on, what are the plans, and so on. And if we take those for given, you can see here the electricity consumption from 2025 until 2050 will be doubled. Okay, so not as much as you saw before, but still it's a significant growth. So we really have an electrification path. And what is expected to happen is that almost all of them is growing as applications, but I would especially highlight here that cooling is growing. You can see is significant, but the transport will also be growing a lot as we electrify that, as well as you can see something about hydrogen production. So you can somehow identify what I showed before. Now, where is that expected to come from? Also looking into what are the different countries saying in terms of being, in terms of what they intend to do. And based on what the countries are saying, here is, let's say, a prediction of where is the electricity then coming from. And the black one and the red, gray, and so on, this is the fossil fuel. The purple here is the nuclear, which is growing. But then the rest, we can say they are renewable based. And you can see that we are really expecting a significant growth in, let's say, wind, sun, storage combination, and also somehow a little bit in hydropower. So having in mind that what we can do with power electronics, this is really demanding a lot in terms of the technology. And that is illustrated here as a basic system, right? That we have a power system where we produce power, classical one. This we want to be substituted by a lot of renewables, wind turbines, PV especially, but also assisted by storage. As well as, let's say, if we look at it, we have a lot of applications where we try, let's say, where we are electrifying the operation. And in that way, we can say in general that you can see the power electronics is really playing a key role. And last but not least, to mention the transportation sector, where we are really applying a lot of power electronics, both for charging as well as to drive the car forward as such. So a huge amount of power electronics will be needed, combined with, let's say, renewable in order to make a sustainable society. Now, power electronics technology as such have been there for many, many years. Even in the early beginning of the electrification, where we had mercury arc rectifier, vacuum tube rectifier, tyrotron. But the big breakthrough came in '57 by the Flaristar, where we by silicon could make a PN structure and really conduct, and we could control electrical power with a high efficiency. And since then, '57, so this is close to, let's say, 70 years ago, you can see that new devices have appeared, and today we are much more in the wide bandgap device area. If we look at, let's say, the power electronics technology as such, there's no doubt that let's say, the technology was looking for super efficient and reliable components. And that came in '57. And from '57, maybe until 2000 or so, there are a huge amount of new topologies, control modeling methods, and then means to increase switching frequency, reduce losses, in digital control and so on, which was really moving on. And there a lot of basic innovation were coming. And then afterwards, I would say that what we are having of driving mindset is that we really try to improve the different applications step by step by doing different things. For example, EMI, EMC, digital twin, digital control, reliability, lifecycle performance, and so on. And we do not see so many new power circuit topologies. And in parallel with that, I will just mention that what is also going on in that respect to make, let's say, products lower cost, higher reliability and so on. And the reliability engineering discipline has also been evolving over time and becomes more and more advanced, sophisticated, where the main thing is that it becomes much more, let's say, physical oriented, physics based in order to describe and understand the reliability of power electronic circuits. If we look at the power electronics, now I would say it's extremely hot area, which one of my next slides will show. But if we look back in history in terms of power electronics technology, when I was a freshman and worked with power electronics, the big thing at that time, that was motor drives, industrial application. And motor drives is super, super important because it consumes adjustable speed drives motors, it consumes 60% of all electricity. So it is important. And this was driving the technology from the 80s, 90s. Then from around 2000, the renewable really start booming and not exploded like we see maybe things of today, but that was where a lot of new innovation came in order to do a grid connection. Now, since 10 years ago, the automotive sector has been moving and driving the power electronics area to a large extent, and still will do, because we are seeing in many countries a boom in terms of automotive based on electricity. I can tell you in my country last month of March, more than 90% of all new cars were based on EV technology. However, the idea was also to look a little bit forward and what is really booming for the moment. And this simplified diagram, in my opinion, is indicating where major things are going on, but I will also mention a few others. There's no doubt the generation side is moving fast, including storage, and I have some numbers which you'll see later. Then energy saving drives is a big thing, the electrical vehicles, as I mentioned. But then as we really want to decarbonize our electricity consumption, we also need to go a hydrogen path in order to have some high energy density application, as well as what we see really booming a lot today, seen from a load perspective. Those are the data centers, in order to make our life better, if we can say so. And the data centers, many of them are applying AI in order to help us to solve problems. The general key drivers of the technology you are seeing here, this is energy efficiency. This is cost of energy, as we really try to lower that. Life cycle cost, as we really try to look at, okay, what is the consequence of using the technology? Predictive maintenance in operation. And when you are in the, let's say, industry side, then time to market is also a key. And some of the things to be able to master, this is the combination of having a product and product when in operation, you have service, and in that way double income. And other things are data, use the data available, and that includes also digitalization, as well as the data, think about the physics as such. If I should highlight some of the main emerging areas of today where we look at power electronics, renewables, transportation, energy efficiency, power to X, also this hydrogen path, data centers, but also the grid infrastructure, because you should remember that we want to double the electricity consumption, and that is going to happen. So this cannot just happen without, let's say, making a grid infrastructure which is modernized and able to deal with it. Storage in different levels, automation is also a key, defense, which is, we see that today with all those places around the world where we do not have, let's say, a safe world. AI is a big thing. Sustainability, I think this is also important to have in mind. Not only think, it is an important aspect to have in mind. as well as energy access to everybody in order to bring prosperity into the whole world, as hundreds of millions of people do not have, let's say, access to electricity, but can really make the life different. Seen from a generation perspective, let me illustrate, for example, in my country, what has been happening over time in terms of where is the electricity coming from. What you can see here, this is the electricity consumption in the last 20 years in Denmark. And the black one is coal, purple is natural gas, and then also some oil. But the rest, this is more or less renewable. And what you can see is that we have phased more and more out coal, and this is coming almost to zero, while, let's say, the renewables has really been growing a lot. And the renewables for the electricity generation in Denmark is more than 75%. And often the generation is plus 100% compared with the load. So we have a society which is moving much more towards being, let's say, a low carbon energy system. What is also worth to having a look at here is that we have almost a constant electricity consumption. This is now going to grow a little bit more thanks to the data centers, but at the same time we have had a GDP growth of 2% every year. So you can try to calculate that, and you can see that our efficiency has been dramatically increased, even though the GDP is growing. If we see the renewable generation from a top perspective, what I show here is this. This is the global energy installed capacity of renewable, of solar, wind, hydro, bio, geothermal, and marine energy. And by today, we have installed more than 5,000 gigawatt of capacity. And yeah, it's really a high value compared with, let's say, what we saw for 25 years ago. Then it's of course interesting to see what is the capacity installed per year. And you can see the market in 2025 was 700 gigawatt of installed capacity in terms of renewable. And the green one is, let's say, the most one. This is in this case the blue one. You can see here. Initially, see from a renewable perspective, the wind was the growing one, while the solar then came, let's say, around 2010, and since then it has really been exploded. So you can see that the blue one is almost exponentially growing, and this is of course thanks to the let's say the cost reduction of the technology. If we look at the wind power development seen from a technology perspective, this is as such very amazing, where in the 80s we had 50 kilowatt, in the 90s 500 kilowatt, in 2000 maybe 2 megawatts. So we have increased the size by 40 times in 20 years. And then if we look at where we are today, we have increased the size by even more. Also, not the same number, but we are now 15, 20 megawatt of sizes in terms of technology. This is not always the most, let's say, cost efficient for especially onshore to make it just bigger and bigger. This is mostly interesting in offshore, because there you can sail, let's say, the units and locate them in the ocean. What is interesting here, seen from a power electronics perspective, is that in the beginning we do not spend much money on the power electronics technology, but after, let's say, 2000, two things pushed it, and that was one. On one side, that in order to interface to the grid, there were certain requirements, and in order to be able to do that, we needed to have flexibility, and the power electronics was doing that. And then at the same time, when we had power electronics in, we could do variable speeds, and if we can do variable speed, then we can harvest more energy, as well as we can make better control of the drivetrain. So there was also many arguments to introduce it to the let's say to the generator side. So the role, as such, we can say, is that today, thanks to the technology of power electronics, the wind turbines are both active contributor and stabilizer. The two technologies most often used are illustrated here. One is what we call a full-scale power electronic-based system, where we have an AC to DC converter to deal with the speed and energy harvesting of the wind turbine, and then to the grid side we have another DC to AC converter, where in between we have a DC link capacitor, as a voltage source converter, and then be able to contribute as to feed the power into the grid in a proper way. This one here is super flexible and also convenient, because we somehow can decouple more or less the operation from the grid side and to the generator side, and in that way deal with if something happens either at one or the other side without that the other side can see what's going on. But the disadvantage naturally is that we have to convert the full power twice, and then the cost will be higher. We are seeing a trend more and more towards this one here. The most popular one has been this one here, where we have a double-fed induction generator system, while this one here can be a synchronous generator, induction generator, or permanent magnet synchronous generator. This one here, double-fed induction generator system, there the power electronics are only dealing with up to, let's say, 30% of the total power, but can do variable speed around the synchronous speed. So it only have to be rated up to, let's say, 30%, meaning that the power electronics expenses are lower compared with this one here. Let's say the challenge on the long run, especially when we scale up in power, the grid requirements are becoming more and more strict, is that we have a direct connection of the data into the grid system, right? So what we see on the grid can also be seen at the generator, and we need to deal with that and be sure that the mechanical part is not having too much overload in case that we have, let's say, low voltage right through and so on. So this is the system which is cheaper, but has a little bit more challenge. But depending on, let's say, the whole plant configuration, this is also a feasible solution and seen in many applications. If we look a little bit upwards in terms of, let's say, what are the alternatives of what I showed before? What I showed before is typically, it could be a low voltage wind turbine where we have, let's say, multiple parallel converters in parallel, and we have a transformer up to, let's say, 66 kilovolts, and then we have a collection grid. This is a very classical technology. As the power is increasing, then it's a natural thing to go beyond 690 volt, because 690 volt is very convenient seen from a safety perspective. If we go up to the medium voltage, then maybe we only need one converter, maybe two, because there are some advantages, for example, in terms of redundancy. But anyway, what we need in such cases still a 50-60 hertz transformer to interface to the collection grid. But here the current in the generator and also in general will be low, and that's seen from an efficiency perspective interesting. The next generation could be, let's say, a high voltage wind turbine, meaning that we are avoiding the transformer you see here, and then go directly to the collection grid, and then have here an AC to AC converter and a generator, which is also high voltage. There are clearly advantages, but some of the challenges are naturally safety, how to do a short circuit protection as well as insulation system. But there are definitely many also interesting features as such. This can be further scaled up if we really want to do the substitution of wind I illustrated for you on the slides before. then we have really to scale it up. And in some countries, it's very attractive to think about putting the turbines offshore, also in the ocean, because the wind conditions are super. And there, if we have relatively, let's say, low depth, then it could be convenient to make an island where we gather all energy together from different plants, make an electrical infrastructure where we then collect the power and then send it by HVD to different countries and such. And we could also imagine that so we do an island here that in some cases it could also be convenient instead of, let's say, for example, doing hydrogen shore where we transport the power, then we could maybe do hydrogen on the location of the island, and then, let's say, ships or a H2 pipeline was, let's say, accumulating the hydrogen and storing the hydrogen which was created. If we look at the photovoltaic, this is also going in a, let's say, a very positive directions. What is maybe most important to highlight in this figure here is, the two most things are, there are many technologies in terms of photovoltaics, right? As we go directly from sun to electricity. That is one thing. And a second is that the efficiency becomes higher and higher. And for some of them, we have a very, very high efficiency thanks to new technology and so on. But let's say the most, important technologies for the moment typically have an efficiency around 30% and also. And of course, it means a lot in terms of footprint. For the PV, we can say that the PV is, let's say, more flexible because compared to a wind turbine where you have to invest in multi-megawatt, here yourself you can invest in a panel or multiple panels and then buy a converter and connect it to the grid. So this is much more easy scalable for a person. It's more easy to come to as a person. And that can be one of the reasons that we see this significant growth in PV compared with wind. And if we look at power electronics role as such, we have here four different, let's say, configurations. Module converter with converters directly to the module, a DC grid with a module converter. Then we have a string system, multi-string system, and here we have a central system. You can see for all of them, we really are applying a lot of power electronics in order to interface to the grid. So seeing from that perspective, there are a lot of opportunities. And here are shown some of the examples of PV inverters, which are very, very popular, have been popular. What is, of course, the important thing is that we have not galvanic isolation, because then we can save a lot of material and so on. And this one here is a very, very famous one by today for higher power applications, where we have a 3-level converter, and in that way deal with relatively high voltage. If we look over time, how the evolution have been for the renewables, you can see here what has happened with the levelized cost of energy for in general all kinds of let's say renewables. And those two technologies, which are concentrated solar power and solar PV, as well as this one here, offshore wind, all of them has really seen a significant drop in the prices. Especially the solar PV is very, very cheap today, and competitive on a large on many scales in terms of implementation, also compared with fossil fuel. In that context, when we want to lower the cost of energy, the reliability is of course also a key, right? Because if we have too many failures, then we have less production and we need to do maintenance and so on. So we really need to have tools for doing reliability engineering. And here is shown a little bit crowded slide illustrating at which phases where we can do something in order to increase the reliability. And the reliability as such is okay, but the lifetime can maybe also be extended. So instead of being able to operate 25 years. If we can operate the same plant 30 years, then you can see that the levelized cost of energy, of course, will be lower. And so here are a typical operational flow of reliability engineering tools, both in design and manufacturing, also in operation and maintenance, and as well as being thinking of, okay, how can we reuse, let's say, what we have been creating when we did, let's say, a PV plant at a certain scale. So recycling and reuse is also a key thing when we look at the power electronic systems. And as we are going to expand so much with power electronics technology, there is also, in my opinion, and also having in mind the Sustainable Development Goals, we have, let's say, an obligation to think of how can we look life cycle wise on the power electronics technology. Here's a classical way of how to deal with making a product where things are ending with e-waste in a remote place or something like that. And we have definitely climate impact as well as pollution and so on. And what we say, normally what is said today is that less than 17% of all, let's say, electronic products of today, they cannot be reused. So we really have to think new in that sense that, okay, we need to do material, manufacturing, packaging, use, and then at the end we have end of life. But then when we do the design, we should think of, could we reuse it for something, or could we refurbish, or could we remanufacture it, or could we recycle the material or something like that? And then in that way, let's say, to reduce the e-waste and of course also reduce the carbon footprint. And in that context, we have to look life cycle wise. And for example, what we could look at was the CO2 impact as such. And here are two different designs. One design maybe is not the most, let's say, efficient one. And it's cheap to build. And then over time, you can see here, because the efficiency is low and so on, then the impact becomes higher compared with a product where, let's say, in the beginning, the cost was high, seen from a CO2 perspective, but thanks to, for example, a higher efficiency, then there can be a break-even point where this other design, which is much more sustainable, seen from an efficient perspective and so on, then this will be, let's say, better in this calculation. And for me, this is one of the future things to be looking at. And that means, of course, when we do all the, let's say, design and installation and so on, we should take this into account. And then what this will be, in order to be able to reuse, this will be a battle between, let's say, a highly integrated system with let's say, a less integrated system. Here you can see a very dispersed, let's say, power converter, which of course is not useful so much in practice, but just illustrating that we have a constraint trade-off between performance and circularity. An example of, let's say, this way of thinking, what I have taken here is wind turbine from the wind turbine manufacturer Vestas, where they every year, where they have some sustainability figures for their wind turbines. And I think that's worth to try to look at. Is a 4.5 megawatt lifetime, 20 years. But they really try to look at, let's say, how can they reuse what they're doing. And the wind turbine recyclability weight is 98%. So that means 98% of the weight can be reused. This is one number out of many. It's really worth to study it. But also the, let's say, the wind plant, how fast it's able to return its energy compared with what it costs to build it, and from mining and so on. This is 6 months. So after 6 months, this is really contributing to the Earth's energy balance, if we can say so. Another example I have mentioned is this, let's say this was more the renewable. Now we were also discussing this hydrogen path, and some places are calling this power to X as electrical power to something else. And what could that be? This is illustrated here, and the thinking is that we have renewables, we have let's say we have a hydrogen electrolyzer, something like that, and then we do something afterwards where either we support chemical processes, industry, we do oil, or we let's say we do fuel, or we do in general electricity based on this X and so on. And in order to do some of those things, we can use biogas methanization, and for methanol production and so on, we need to use CO2. We have to capture CO2 and bind it with a hydrogen, and then we can do the rest. And in that context, in order, let's say, to be able to do that, you can see that the power electronics is key in order to be successful. And that is, of course, something to have an electrolyzer, which is DC, and then we do AC to DC conversion, and we typically need to let it be galvanic isolation. And just thinking about it, as we need a huge amount of conversion power in order really to make a difference in terms of, let's say, energy intense applications. And what I just try to put on a list here are some of the requirements for a unit like this, and also what are the challenges if we are going to make and when we are going to make power electronics for such kind of technology. The main challenge in general for this way of going power to X are the electrolyzer themselves, because the conversion efficiency there is not super high. There are three main technologies, where one of them is high temperature solid oxide electrolyzers, where the efficiency can be high, but the other two relatively high, where the other two are much less, and we are losing a lot of, let's say, energy to do this process. So this is not a super efficient, let's say, process, but it is a needed process in the cases where we cannot find alternative ways in order to substitute that. And that could, for example, be, let's say, fuel for airplanes and so on. Here are shown two converter technologies, like you saw some converter technologies for the wind turbines. And ideas are coming, let's say, from other applications, aluminium furnaces and so on, where we use 12-pulse transformers and then rectifiers, and then a buck converter system interleaved. We can do active rectifier instead of diode rectifiers here, and then in that way have relatively high quality current compared with the other one, where we are using a 12-pulse transformer and then a trap filter. So there are pros and cons, and dependent on what are the specifications, one can be more, let's say, attractive compared with another. I will just advertise a little. What I'm spending a lot of time on now is, let's say, to see how we can improve the material for doing this power to X. And I'm a part of a center at the Technical University of Denmark called CAPEX, Center for Accelerating Power to X Material Discovery. And if you are interested, take a look there and some of the things going on in that respect, because I think material is very important. Now, what is also, let's say, a challenge in general is as we are expanding the grid, there are two factors. We have to have more power flowing there, right? Double. Plus, we are also introducing a lot of more units in that respect. And here is illustrated just as a principle. You can see to the left here, generation, to the right, consumption, and also liquid. Well, what we can see is we have power converters, we have filters, we have cables, we have connections, and there is, if we are not careful, a risk of that we have interaction between them, and we need, let's say, to be able to predict and handle if we have, let's say, interaction between the different converters. And looking at what is happening when we are introducing all those power converters is seen from a time scale perspective. That here you can see from let's say very short time to longer time. Let's say the time dynamics we typically deal with. And then we come with the control dynamics of the power electronics, including the filters and so on. And you can see that we have a new area which we need to be able to take into account when we are coming with so many, let's say, converters connected to the grid. So, of course, we need to deal with angel stability, frequency stability, and voltage stability in order to say something about, let's say, the power system stability. But we also need, let's say, to be able to see if there are any harmonic interaction between the systems. And as mentioned, the grid is going to expand. So we really have to come with the tools. And here is illustrated how much transmission system is going to be built in the next 25 years and how much distribution system is going to be built, where we are talking about million circuit kilometers. So you can see it is more than a doubling. In both cases, distribution is, of course, becoming more expanded as such. So we have to be able to deal with it. And the question is, of course, should we just continue to increase size and, let's say, just think of a constant frequency, we are controlling the frequency, or should we think a little bit different in terms of that? Because if we have a failure in a grid which is double size or something like that, then if we have a big failure, then this can be dramatical, because then many consumers will be affected. And for that, I'm working together with some other professors about, let's say, looking at if we in some smart ways can apply, let's say, new methods using power electronics and storage, and in that way somehow more decouple the power system, so we do not just have one monolithic system. So the monolithic system is illustrated here, you know, top down power from high voltage level to low voltage level. And the thinking is in the project that, okay, you can see we have the transformers here. Maybe we can make some subgrids, asynchronous grids, where we by transformer technology, for example, smart transformer, is able to decouple so they can take care more of themselves. So if something goes wrong at the top level, then this cannot be seen here, at least for days or something like that. And in that way, then, if needed, then connect fully to the grid system. And such kind of thinking is somehow implementable over time, and you do not have to revolutionize everything. And then the long-term vision is that we are implementing the system with, let's say, a more internet like structure, where we have a lot of smart transformers, and interaction can easily be between the different A grids, and they can also be up to the top level, and in that way not just build one monolithic power grid. So let's say the thinking is a little bit like the internet, that let's say we have LAN structure, we have IP, we have TCP, we have apps, application, and so on. And that could be thought a little bit like asynchronous grid here, local balancing of energy, global streaming of energy, and then also smart power application and pricing, which is equivalent to some apps we can have on our let's say on our mobile phone and so on. So what is really needed in order to be successful in that context is naturally, of course, the ability to swap the transformer here, which is absolutely important, and so on, to be, let's say, substituted to be more, let's say, smart transformer-like, where then, let's say, in a more flexible way, we do the interconnection between the system, and the scalability on the long run and cost is, of course, an important part. So thinking a little bit out of the box and thinking into the, let's say, the safer grid area, we have tried here to look at what are the classical way of, let's say, doing the operation of the power system, where fundamentally everything is about power equilibrium in order to have the frequency, while the next, another way of doing it is more to think about the balancing of energy in those asynchronous grid. And here you can see, let's say, the different layers and their advantages. One of the other areas I want just to touch on in terms of my presentation today, this is the application of AI in power electronics, because I illustrate that also in the beginning. And the AI is really booming a lot. There are so many new things coming, so it's really hard to follow. And I would say the machine learning AI, yeah, computer vision is extremely accepted. There are also some areas where this is just on the way to be useful. And here is the Gartner diagram of that. And here, let's say, here are, let's say, some of the important, interesting foundation models, Edge AI, and many other aspects. And just to illustrate that there are so many things we could imagine that we could apply in power electronics. If I should look at the application of power electronics, I would maybe illustrate it by this diagram here, where we can apply AI in the design phase for different components and systems. We can apply AI in the operational and in the operational phase, digital twin, condition monitoring, control and optimization. And then at the end, we can also apply AI in a proper way to do, let's say, life cycle assessment and do a strong reusability as such. And the tools are many. There are tools offline, there are tools for online, and those two together, of course, also have to be, let's say, somehow analyzed. And in that context, say something about the uncertainties. And here we, Monte Carlo, Bayesian neural networks, and other methods are having in place. But as you can see here, there are so many possibilities. One thing we have been applying, let's say, machine learning algorithms and such, this has been to describe in an efficient way, let's say, the temperature in chips, in a design power converter, what is the junction temperature when we are simulating a driving cycle in an electrical vehicles. In this case, is in two different places, and then we simulate more than I think it's 1800, maybe 30 minutes or something like that, in order to say something about what will the temperature be in the devices, in order to calculate okay, what is the consumed lifetime of the system. And here we have, let's say, done it in different ways. We have just simulate convolution method. Then we have something we call profile reconstruction. And then we have something where we use dictionary learning, and in that way, in a smart way, to do the calculations. And dictionary learning is in this AI domain. And here is illustrated the four methods simulating different time periods from 10 seconds to 10,000 seconds. And here we can see how long time it takes. Remember, this is logarithmic scale. So here is, if we use Simulink, if we use this convolution method, it takes really a long time. Then we have a simplified method, and then we have this method where we use dictionary learning, where you can see there is some initial learning, but then in order really to scale up the simulation time, it's super powerful. So if we really want to do really long-term assessment, this is the way to go. We could also imagine that we are applying AI in control. And here's a classical way of doing a motor control modulator. We have a motor converter, transformation, some compensation for how the inverter behaves, inner control loop, outer control loop, and then also a flux observer. And we could imagine that we were applying, let's say, machine learning algorithms or other learning algorithms in that context, and see what is going on if we are applying them. And for doing this kind of, let's say, AI-assisted control, what the benefit could be, that we could maybe get better machine parameters, estimate that better. We could have better adaptation to the grids. We could also maybe in a faster way, let's say, do the optimization and operation. And we could also imagine that the inverter, seen from a modulation perspective, is also optimized. Well, I'm coming to an end, and I hope you have got, let's say, some inspiration and ideas. What are the trends in terms of power electronics and renewable generation? But for me, we are really moving into a much more electrical-based society, and the technology we all work with have so many, let's say, performance metrics, and giving us energy access, transportation which is efficient, energy saving in general, and grid connection. As you saw, the wind and solar were very, very competitive, price still going down, but will also be interplayed with storage, in my opinion, also the battery storage especially. Some of the things we should have in mind are, of course, the future power grid, the sustainability. We should also look at how we can improve, let's say, the hydrogen path. How can we do that more efficiently? And we have a huge amount of opportunities in order to apply AI in a smart way. And as I also showed for you, seen from a power electronics perspective, we have many also application areas. So we have a lot to do in the right way. Before ending, let me just give a small advertisement. We have one smaller workshop in Aalborg on wideband gap devices just after ECC Europe. If you have time, you are very welcome. They really try to have low budget, let's say, registration, maybe 300 euro. So in September. And in November, we have another conference from 18 to 20 on November, where we are discussing design methodologies for power electronics. Yes, so with that, thank you very much and for your time, and I will be happy to answer questions you might have.
Thank you so much, sir, for such an insightful and informative session. We truly gained valuable knowledge about power electronics and renewable energy integration, and we also understand the more details about prediction of energy consumption, sustainable energy integration, and also various electrical terms used in the electrical engineering. Thank you so much, sir, for such an informative session. Now, dear participants, if you have any queries related to the session, feel free to unmute and ask a questions.
Hi, Dr. Fred. Am I audible?
Hello.
Okay. First up, thanks a lot for this insightful session. My question to you is, when we consider about renewable energy integration, how can we focus on responsible AI and the implications of hallucinations in the models, if we want to see it across different domains?
Yeah, if we talk about renewable and the application of AI, now my mission here today was to give you ideas, right? And then of course I can have some let's say opinions about how I look at the use of AI in some application. And I think let's say I'm a little bit pessimistic in terms of, let's say, very fast loop control using AI, while I'm more optimistic on, let's say, AI being applied for digital twin, for condition monitoring, and so on. And in those contexts where you have, let's say, those deviations from, let's say, what is true, there we have the possibility to set up some safety things which ensure that the system is not behaving unpredictable, if you understand what I mean. While if you do it in very fast loops and then you can you can hardly be able to react, and then you could have let's say problems in your system.
That answers. Thanks.
You're welcome.
Thank you, sir. Now, from another participants, if you have any questions, please unmute and ask the questions.
Good evening, sir. Am I audible?
Hello?
Am I audible, sir?
Yeah, please go. I listen to you.
First of all, thank you, sir, for that insightful session. My question is that where do you see AI or data-driven control realistically outperforming classical classical control methods in power electronics?
We see it, let's say, where we try maybe to do a little bit more long-term prediction about what is going to happen. Also, there we could imagine that machine learning methods and others could help us, let's say, to predict a little bit more faster into the future, based on more, let's say, model-based approaches. And then I would also think that we will be able to see it in extreme nonlinear cases where, let's say, our classical methods are not enough in some areas of operation, and then let's say trained networks will be able to learn, and in that way to be able to do it. But I would say the time scales are not microsecond. The time scales will maybe be above, let's say some milliseconds, as I see it today. Of course, chips and other things can do something also to speed up things, but that would typically be where I could see it, as above, let's say, 1 millisecond loops, maybe even 10 milliseconds, and slower. There I could see some perspectives of applying AI in a large extent, especially when it's very nonlinear. You should not use AI if you feel your performance is okay.
Thank you, sir.
Thank you, sir. Now, another one participant who is interested to ask a question, please unmute and ask the question.
Hello, sir. I am audible.
Hello.
I am Anga. Sir, session is too much good. My question is, how does power electronics contribute to smart grid development?
Yeah, very good question. And the smart grid is of course many things, right? Also, this is from the basic converter you are connected to the grid up to the overall system operation and optimization and so on. But I think the power electronics contributes almost on all levels, because the power electronics, because we can control the electrical power instantaneously, really give us a lot of flexibility for the operation. So the smart grid and the controllability would never be possible without, let's say, the power electronics. And this can be the converters which are producing power into the grid. This can be the consumption, which is controllable through power electronics. This could be, let's say, the transmission and distribution, as for example, the DC transmission system. This is also power electronics, right? And this gives flexibility. So for me, for the smart grid implementation, the power electronics play a key in order to be successful.
Okay, sir. Thank you.
Thank you, sir.
Yeah.
Now further questions, then ask questions.
We have one question in the chat by Supriya Kulkarni ji. She has thanked you for this amazing session, and she has asked whether you can share some reference paper or related links for your research work.
Yeah, as you mean the presentation here today, I can share with you the slides, and two last slides. There are some references, or maybe three. There are some older references you can try to get. So I have this. I have the slides here where there are some reference at the end. So I'll be happy to share them.
Great. Thanks, sir. Thanks, Supriya, for asking.
Sir,
Yeah.
now I request participants, as we have any questions, then ask questions. If you have any queries related to the session, please feel free to unmute mic and ask a question.
If there are no questions, you may go ahead.
Okay, sir. As we move further, if any participants have, as we move further, if any participant does not have any questions, then I now request our technical partner, IEEE R10 representative, Professor Kirtiraj Garudialar, to address the gathering and share his valuable thoughts with us.
Sure. Thanks a lot. Before we go for the artificial intelligence collaboration related aspect, there's one question which is in the chat by Dheeraj Patil ji, who has asked, who has first thanked sir for this wonderful session. And his question is, what are the limitations of doubly fed induction generator system compared to full scale converters? If you may share some light on it.
Well, you can imagine the stator is connected directly to the grid. So if you see voltage drop, if you see asymmetrical voltages and so on, then of course you'll see this more or less on the stator side, right? So this can be one of the limitation, being able to deal with those situations as such. And then in most of the GFID systems, there is an electrical connection to the rotating part. This can be done in other ways, and that means there can also be some maintenance compared with the other one. While the other one, of course, has the disadvantage that you have to convert the full power twice, right? Because if it is a 5 megawatt generator, then it has to convert 5 megawatt, and this 5 megawatt also have to be sent to the grid system. So they are some of the main, let's say, advantages and disadvantages.
Hello everyone. This is Vijay Shetty. I have a question for you, sir. So I just want to ask you, what are the biggest real-world challenges the utilities face today when integrating high levels of renewable energy into existing grids?
Uh, yeah, that can be that can be, let's say, analyzed on different time scales, if we can say so. Seen from a long time scale, of course, the variation of wind and sun over, let's say, a day, or dependent on, let's say, how the weather systems are, then wind and sun is not constant, right? If you talk with so there you have to deal with this kind of production type, which is possible, but you have to deal with it. So this is challenge, not necessarily the biggest challenge of today. I think today, at least in my countries, what we have of biggest challenge is maybe the capacity of the grid. So this cannot follow the pace of expected growth, because it takes time to expand the size of the grid. And that combined with that we have, for example, the data center loads. This gives a lot of challenges for the utilities, both at distribution and at the transmission level. So the expansion of the grid, I think this is for the moment, as I see it, to be able to cope with this many installations.
Yeah, that's a great answer.
We have problems in Denmark because not so much of the generation for the moment, but for the moment those data centers make a lot of, let's say, demands to the capacity. But also in general, I say, if you have to double the size of the grid, how to do it, new grids or parallel grids, or how to do it, and that really take a long time. And you should remember, this is in 25 years, and 25 years is long, but it's also short when you have to build up such capacity.
Yeah, what you're saying here is like very deep and important, I believe. Yeah. Thank you for your answer.
You're welcome. Very good question. Very good question.
Yes, sir. One more question is there from the chat box. So, can AI detect faults faster than traditional protection in decentralized grids?
Yeah, I think over time we will see examples where over some time, some learning about how things are look like in the grid, and then we can predict that some failures are going to happen before they are happening. This I'm quite optimistic on, that we can get a more reliable, faster, earlier warning on if in some failures are coming, and when they come, then we also know better what to do with the failures. So, but I do not have super example. I think I have read some papers, but I'm quite optimistic that we will be able to see some smart solutions there.
Dheeraj Patil, you might have received a positive answer from the resource person, it seems.
Yeah, it has been a pleasure.
Yes, sir. Thank you, sir.
Thanks a
And
lot.
one more question came, sir. How do we AI decision explainable for grid operation?
How do we make
AI decision explainable for grid operation?
That's, I think, yeah, so this explainable AI, I think, is the thinking, and the combination of part physics, we should not treat the grid as a black box. We should treat the grid as what we know, and then the deviations which we are seeing, them we use, let's say, in a smart way on top of it in order to make the models better. This, I think, can be a very promising way to go, for example, in order to have a digital twin of a model for using it to, let's say, to protect and to operate it. So I could imagine explainable AI could in a proper, let's say, management be useful, a useful way of operating the grid.
Archana, continue, Archana.
Thank you, sir. Now, from participants, if you have any questions, then feel free and ask questions.
Sir, one more question is there from the chat box. So what are the most important software tools a student should learn to excel in power electronics?
Yeah, I think MATLAB, Simulink, Plex, as all the control tools, I think they are very good to learn from. Also to be able to simulate the behavior of circuits. So if you know them well, I think you are in a good and maybe also PSpice, SPICE circuit related simulation tools could also be of interest. MATLAB is also a good tool for control design and AI, and so yeah. So these are good tools.
Okay, sir. Thank you, sir.
Thank you, sir. Now, from participants, if you have any questions, then raise the hand and ask questions. Please ask questions.
Hi. Hello.
Yeah, hello.
Hello, sir. I'm Ashia. As an electronics student, I would like to ask a question about, in your view, what are the advantages of using AI-based control system in smart grids?
Yeah, I think the AI system can be used to model very strong nonlinear phenomena. I also think AI can be used for identify pattern, so we can, let's say, do some prediction faster than we could do it before, as a forecasting and so on. So I think that could, and then of course also to be able to let's say, to predict faults, to handle faults, where we maybe could apply, let's say, previous situations, and then find out what we should do in the case that we have such kind of events.
Okay. Thank you, sir.
You're welcome.
Now, from participants, if you have any questions, then raise the hand and ask questions. If there is no questions from participants, I would like to invite our technical partner, Professor Kirtiraj Garudialar, IEEE R10 representative, to share his valuable thoughts with us.
Thank you so much, Archana and Dr. K. Shivashankar. First up, I would like to raise in honor of Dr. Freddie Blaber Jurg, who has accepted this invite and has delivered such an informative and enriching workshop for all of us. Thank you so much, sir, for your valuable time. It has been a great learning for all of us. Here, I represent IEEE Region 10 Asia Pacific Artificial Intelligence for Power Systems Global Coordination Committee. This committee was formed and constituted under the chairmanship of Dr. Fran Lee, who is the global chair of this committee. And this initiative brings up all the artificial intelligence initiatives under power and energy global society under one umbrella. Whatever different technical events are happening across the globe in special interest groups or technical activities groups or educational activities, AIPACC aims to bring all those things together so that people have better growth opportunities and learning initiatives. At the outset, I would also like to thank Srinagar College for this great initiative, because in terms of learning through IEEE, where we advance technology for humanity, it becomes very important to learn from distinguished lecturers and guests like Dr. Fred. Thank you so much, sir, for your valuable inputs. And also, we recently had IEEE Power and Energy Society Day celebrations 2026. So, for all the participants who have joined in today, happy PES Day 2026. Thank you so much and have a great time. Warm
Thank you,
regards.
sir.
Warm regards, Kirdiraj Garud, IEEE Region 10 representative, AIPACC, IEEE MGA Gold graduate, and a contributor for Maharashtra section and India. Thank you so much and have a great day, everyone.
Thank you, and you too all. Have a nice evening.
All participants, please try to turn on your video. Just we may take one group photo. If possible, all of you, please turn on your videos. All participants.
So we may remove the spotlight and add everyone in the great gallery view.
Yes, sir. Yes, sir.
Yeah, thank you.
Yeah, continue, Archana.
Yes, sir. Thank you, everyone. Now, I would like to invite Ms. Samruddhi to deliver the vote of thanks. Over to you, Samruddhi.
Good evening, everyone. On behalf of the organizing team, I, Samruddhi, would like to express my heartfelt gratitude to everyone who contributed to the success of this international webinar on recent trends in power electronics and renewable energy integration. First and foremost, I would like to thank you, our esteemed speaker, Professor Frede Blabber, for sharing such a valuable knowledge and insight with us. Your session was truly inspiring and informative. I would like to extend my sincere thanks to our respected Principal Dr. K.J. Karande sir, Vice Principal Dr. S.G. Kulkarni sir, and IEEE SB Counselor Dr. K. Shankar sir for their constant support and guidance. I would like to express our sincere gratitude to Professor Kirtiraj Garud, LR IEEE R10 representative, for their valuable support and encouragement. Our special thanks to the IEEE student branch, SKN SCOE, and electrical department, and all the organizing committee members for their dedicated efforts in making this event successful. Lastly, I would like to thank all the participants for joining us and making this technical webinar interactive and meaningful. Once again, thank you all for your presence and support. Have a wonderful evening ahead. Over to you, Archana.
Thank you, everyone, for being a part of this insightful international webinar. We truly appreciate your time and participation. Have a great day ahead. Now, there is one announcement to all participants. Feedback link is sent in your WhatsApp groups. Please submit the feedback and get an assessment link. Thank you, all of you.
Yeah, thank you, sir.
Okay, so I'll move to the next meeting. Thank you very much, everybody. Have a nice day.
Thank you,
Evening.
sir.
Yeah.
Yeah, thank you, sir.
Thanks a lot, sir. Have a nice day.
Bye-bye.